In this lecture, we're going to look at how we can use our method for discrete systems to solve systems that involve electrical circuits. So our governing law in this case is Ohm's law, which is a relationship between current and voltage drop between ends of a resistor. We know it as V equals IR. We're going to rearrange it as our current is equal to our voltage divided by our resistance. We also have Kirchhoff's rule that says the sum of the voltages in a closed loop has to be equal to 0. So again, if we were to draw a single resistor and apply Ohm's law to both ends, we would get that our current at both ends is equal to 1 over our resistance times 1 minus 1 minus 1, 1 times our voltages at our two ends. So we're going to look at an example. We have a resistor circuit shown. We're trying to determine the currents through the loops and the voltage at all of our nodes. So this is where it becomes really important on trying to see how all of the elements in our system connect together. Instead of writing out the equations over and over again, we're really going to pay attention to this picture and how everything connects. So this is going to be 6 by 6. Okay. So every column represents a global node, and every row also represents a global node. So for the diagonal, it's what is at that node. So for example, we're going to start with node 1, and at node 1 we have spring 1, resistor 1, so element 1, and we have end 1. So now we're going to look at node 2. So what do we have at node 2? At node 2 we have resistor 1, N2. We also have resistor 2, N2. We also have resistor 5, N2. That's a 5. If we were to look at global point 3, we have resistor 2 and 1, and we have resistor 3 and 2. And we keep going with 4, we have resistor 3 and 1, plus resistor 4 and 1. At point 5, we have resistor 4 and 2, and resistor 6 and 1. We also have resistor 5 and 1. Then at point 6, we just have resistor 6 and 2. Yes, if you had completely numbered your picture differently, you're going to get a completely different set of you're going to get a completely different looking coefficient matrix. So for the next one, so for the off diagonals, we're really looking at what connects point 1 to point 2. So what connects point 1 to point 2? Well, that is resistor 1, and from point 1 to point 2, it's end 1 to end 2. Now the nice thing about our coefficient matrices are that they're symmetric, so I can just fill in that one. So to do the next one, what connects points 1 and point 3? So here's point 1, here's point 1, and here's point 3. If nothing directly connects the 2 points together, you put in zeros. Okay, so let's look at our next one. We have point 2 and we have point 3. Well, connecting points 2 and points 3 are resistor 2, and that's 2 to 1. Again, I'm going to take advantage of my symmetry to fill in the diagonal. Nothing connects points 2 to points 4, so I'm going to put a 0 in there. Something does connect point 2 to point 5, which is resistor 5, so I'm going to put in a K5, and it goes from 2 to 1. Nothing connects it to point 6, so I'm going to fill in the rest of my column. So now we have what connects points 3 to points 4. Well, points 3 and 4 are connected by resistor 3 from 2 to 1. Nothing connects 3 to 5, and nothing connects 3 to 6. So now we have what connects points 4 and points 5. Well, points 4 and point 5 are connected by resistor 4 from points 1 to 2. And nothing connects point 4 to point 6. And lastly, I have what connects points 5 and 6, and 5 and 6 are connected by resistor 6 from 1 to 2. I'm going to go fill in my bottom half of my diagonal. So really, with more complicated systems, you want to be able to look at the picture and be like, how can I generate my coefficient matrix without having to write out all of the equations? So our governing systems of equations in this case, if I put on my voltages, V1, V2, V3, V4, V6, it's going to be equal to my currents, I1, I2, I3, I4, I5, and I6. So the next thing we need to do is apply our boundary conditions. We know that V1 is equal to 200 volts. We know that V6 is equal to 0 volts. And we know that I2 is equal to I3, which is equal to I4, which is equal to I5, which is equal to 0. Because again, they are all in the same loop. And that is what we have from our electrical knowledge. So now we have to condense our system down. So to condense our system down, I want to get rid of rows and columns where I know things. So I know V6 is 0, and I know V1 is 200. So I want to be able to get rid of column 1 and column 6. I also know that my currents 2 through 5 are 0. To keep my matrix square, I'm going to get rid of equation 1. I'm going to get rid of equation 6. So I'm going to solve for my unknown voltages before going back and solving for my unknown currents. Now, this is usually pretty simple, but what I want to point out is we have in row 2, we had this K121 times V1. And in row 5, we have this K612 times V6. We have to account for those by moving them to the other side of the equation. So our condensed equations become so we have our condensed stiffness matrix times V2, V3, V4, V5 is equal to 0 plus where I've moved those terms from the left-hand side of my equation to the right-hand side of my equation because I want all of my constants on the right-hand side. If we run the solution, we would get that V2 is equal to 169.23 volts. V3 is 153.85. V4 is 146.15, and V5 is 123.08. So to find the unknown currents, we're going to go back and solve for using our equations 1 and our equation 6 that we had previously ignored. So we're going to current 1, which is equal to 0.2 V1 minus 0.2 V2, which is 6.154 amps, and I6 is minus 0.05 volts times V5 plus 0.05 times V6 is minus 6.54 amps. We can also solve for the current in the elements. So the current in element 5, so I5 is equal to 0.1 minus 0.1 times V5 and V2 So we have the current on both ends of resistor 5 are equal and opposite as they should be. And then I can do it for resistor 3 as well. So it's very similar to the methods that we use for springs, rods, and torsion. Now we're doing it for circuits, and really the idea is to be able to generate the stiffness matrix without having to write out all of the equations every single time.